Hello, this is Team 2. Our members are 구인혜, 곽찬신, 오성룡. Let us start our proposal presentation. This paper published at Intelligence Robots and Systems in 2022. This suggests the off-policy actor critic MARL method named Darlin. Darlin solved the problem that more agents increased the computation dimensions. The solution of paper keep policy quality while decrease the computation demands. This key idea is training with neighbor agent, not all agent. This simplify the Q function. Let us introduce previous approaches to solve same problem. There are 4 SOTA MARL algorithms. Those are training with all agents. So more number of agents cause more computation tasks. As first trial to solve this problem, there are 3 ways to reduce complexity of Q function named VDN, QMix, and QTran. Also, there is a way to decompose global Q function into local value functions. To approximate the local value functions, there are 2 algorithms named MFAC and SAC. The Darling used SAC algorithms in case of k equals 1. So also use graph structure for distribute training. To understand the paper in detail, let us tell you about rainforest running briefly. This is the background for MARL algorithms. This is the process. A joint action at time t applied at state at time t and triggered transition to new state at time t plus 1. After each transition, each agent I received the reward. The objective of each agent I is to choose to deterministic policy mu I and an optimal policy mu I for agent I can be obtained by maximizing the action value function. This paper imposed additional structure on the MARL algorithm, a problem. Assume that all agents share a common state space, define the disk proximity graph based on distance and the distance function between states. Also make the following assumption about the distance reward and transition model of agent I.
Now let's talk about how Darlin approached this problem and how it achieved better performance than previous works. As the name, distributed MARL with one-hop neighbors implies, their main idea is to limit the interactions among the agents within one-hop neighbors to reduce the learning complexity. Simplified procedure described in Figure 1a. At each time t, each agent calculates their one-hop neighbor set Ni and also consider potential neighbors Pi to describe the next time step's one-hop neighbor set, and they only consider interactions among these neighbors. Also, they additionally adopt distributed training framework with replay buffer. When actually implementing the parameter update, agent I only needs training data di from its one-hop neighbors at the current and next time steps. These data dynamics obey the following proposition. Under assumption 1, if an agent j is not potential neighbor of agent I at time t, it will be not a one-hop neighbor of agent I at time t plus 1. This allows us to decouple the global interactions among agents and limit message exchange or observations to be among one-hop neighbors. So we can do parallel training that each node only simulates the subset of agents. That makes distributed training much more efficient than previous approaches. Detailed final algorithm is as follows. For evaluation, Dave used 4 environments: icing model, food collection, grassland, and adversarial battle. These environments cover cooperative and mixed cooperative competitive games and provide opportunities for watching multi-agent interactions. For benchmarks, they've used MADDPG, MAFAC, and EPC as baseline. Here, SAC is not included because Darlin is actually distributed training version of SAC. For evaluation metrics, the paper wanted to compare the training efficiency and police quality of algorithms. To see training efficiency, they've checked average training time and convergence time, which denotes how fast the algorithm learns. For police quality, they've used convergence reward. Here, convergence reward is the average total reward at the convergence time. So if the convergence reward is high, we can say that algorithm works better. The following tables describes the convergence time and convergence reward in each environment. Better numbers are marked as bold. They measure the result while varying the number of agents. As we can see here, in most cases, Darlin worked as best among baselines. Also, as we expected, average training time of Darlin greatly outperformed other algorithms.
This is the end of our paper introduction, and now let's talk about why we think this paper is interesting and why we chose this paper for the project. Since we are working on computer systems research, we are interested in the multi-node parallelization and scalability problems. Also, we mostly learned a way to control a single robot during the class. It was great, but also got us wondering what happens when we've got a bunch of robots to control in the environment. So we've searched for papers that treat multi-agent problem. Finally, among the MARL papers, we've selected this paper, Darlin, because it describes the efficient distributed training scheme and suggested novel working methodology to overcome the curse of dimensionality in multi-agent problems. Then we'll move on to how we'll reproduce the paper. The paper GitHub exists and the codes are uploaded. While preparing this proposal presentation, we've tried to check whether the provided code runs well, and we've finished setting the server to run the code. One big problem while reproducing the paper is that we cannot use multi-node server. So the reproduced result may differ from the paper. When it happens, we'll try to emulate multi-node environment using multi-core or NUMA concepts. This would include emulating network latency and other factors. This would include emulating network latency and other factors. Finally, we'll finish the presentation by telling how we'll improve the paper. For paper improvement, we are planning to take two-step procedure. First, we'll change the code to use two-hop neighbor states and actions instead of one-hop neighbors one. This will lead to the increase in learning complexity, but also it will be able to find better policy. As a result, we expect to observe the trade-off between learning complexity and performance. Secondly, we would like to suggest neighbor hop selection algorithm. We expect that changing hops would affect the result differently with respect to the environment and the configuration. So we will analyze the environment property that decide the trade-off between learning complexity and performance to find the best fit hop configuration. As a result, we hope to try dynamic hop selection for each environment for the best effort performance. Thank you for listening to our presentation.